So good morning, everyone. I am Jérémy Rohmer from the French Geological Survey, and we'll do a presentation more focused on application and focus on coastal hazard assessments. So what are coastal hazards? You can see that on the four pictures that on the slides. We are speaking about rock falls on coastal cliffs. That's the top left photo. We are speaking about shoreline evolution due to here the problem of storm Xynthia 2020 on the Atlantic coast. We are speaking about problem of marine flooding, either from waves on the left or on the right, the inundation, the flood extent due to the famous Xynthia 2010 storm. So in this context, oh yes, it's working. In this context, the computer codes are the key. What you see there is a nice video of my colleagues. I don't know if I can come back, maybe show it again, I don't know. And yes, that's the work of my colleague focused on numerical model, and they achieve a very high resolution, high fidelity, high precision of the reproduction of the consequences here on the Xynthia storm on this side, that's Arcachon Basin, on the Atlantic coast. So you can see that we can reproduce very well. If we compare to the observation, in situ observation, the numerical code is validated. But the problem is really what I show there. Even using highly parallelized computing architecture, the computation time cost for that kind of simulation, numerical simulation, is 1 day. That's problematic for us because the regulator is asking for quick and rapid information to take action, to take decision. So for the moment, that's incompatible to have a very precise simulation and on the other hand, to have a rapid answer to the problem. So maybe the answer can be high computation architecture. That's what I try to illustrate with the supercomputer at BRGM. But the problem is that if we use all the computer on this architecture, we can achieve a computation time cost for the example of less than 2 hours, which seems to be compatible and feasible to deliver this kind of rapid information to take actions. But the problem is what I've written in red. What about other sites? Here I'm focused only on Arcachon, which is somehow a small site. But if the mayor of La Rochelle is also asking some information, what are we doing? Are we using another architecture to deliver the information? So here we have somehow a problem of small data. We are not in the problem of big data, but really a problem of small data in the sense that we are not able to compute a lot of observation, a lot of realization of such kind of simulation results. So the idea is to rely on this generic approach of surrogate modeling. The idea is quite intuitive. If we have a database of numerical simulation already done on some cases, let's benefit from that, and let's try to train a machine learning model to deliver this quick answer I need. So this approach, this surrogate modeling approach, starts with a simple step, which is called the design of experiment. I have to build my database of numerical simulations. So that's represented schematically by the dots that you can see there in the space of the input conditions. And for me, the input conditions are what I show there in red. That's the storm conditions offshore on that kind of boundary that you can see there. So I have a lot of conditions which define a storm, which define the input of my numerical model I showed you before. And just a remark, we can have information from Météo France, let's say, from their regional early warning system to have information about the storm condition offshore. now I have the input defined thanks to this step of design of experiment. So I can run the numerical simulator. That's what I showed you before. You have another example. It's also working, I'm glad, about a tsunami modeling. But what is interesting is that for any point, you can see there, you have to run your high fidelity numerical simulation to gather information about the indicator of flooding, the indicator of coastal floods. Okay, and now if a new storm is occurring, if you have already this database, if you have done the work of fitting and training a machine learning model, this is what we call surrogate model, we expect to deliver information in the gap where we do not have any information. That's the broad picture of what we're trying to do. And to do so, there are many techniques, of course. We will speak about neural network, but we like to collaborate with Toulouse and colleagues, Olivier, for instance, and we like to work with quotient process framework. So it was nicely introduced by Jan, so I won't go into details. I will just highlight two aspects of this framework. Uncertainty quantification, which is also very nice when we speak about with the regulator about our results. And the second aspect, which is nice with this framework, is the flexibility brought by the kernels. Jan clearly highlighted how flexible we can define a kernel depending on the context of the data, depending on the PDA for his case. I will speak about the flexibility regarding the data that we are using. So that was the big picture. Now, what are the challenges for our case of coastal hazards? The first picture is that the input, the storm condition that I spoke about, they are a bit particular in our case. They are extreme, and they are functional in the sense that we are processing time series. So that's the picture of what we are manipulating in practice. On the left, you have the condition, the functional condition for wind, surge, atmospheric conditions, waves that we inject in the numerical model that we are manipulating. Sorry. And on the right, I try to illustrate that we are using something which is also extreme. And that's two examples of wave due to Gority, a recent storm in January, and you are still experiencing the effect of Niels, but also this illustrates the extreme character of the waves that we have to inject in the numerical simulator. So this kind of problem is challenging to design the experiment, to design the computer experiment that I told you before. Generically speaking, what we expect from a classical design of experiment is to select a number of input configuration, a limited number of one, let's say 100. We try to span a large range of values, and we try to have space filling property. This is illustrated with this toy example. On the right, you have a crude approach where we randomly select in the input domain the configuration that will be used for the numerical simulation. And on the left, you have an optimized way to select those configurations. We try to have this space filling, as you can see, property. So the question we ask, and this is a question we ask to ANITI and to the chair of Olivier Roustan and Jérôme Monnier, PI Learn Water, we ask how to do design of experiment with extreme time series. And that's the PhD of Nathan, who will have a poster this afternoon. And is currently developing the different components to perform the design of experiment. And the first component we are needing is a simulator, a stochastic simulator. The question he tried to address is how to stochastically simulate time series, multivariate time series, but also extreme time series. And that's what he's currently doing. And so just to illustrate such kind of data that he reach, on the left you have the observation and the stochastic simulation he achieved to reach. And on the right, there's some kind of validation of the extreme character of the stochastic stimulation is currently running at different time steps. So if you need more details, of course, see Nathan poster this afternoon. Second problem with time series, the surrogate model. And here comes the flexibility of the kernel. So I don't have scalar inputs as input of my Gaussian process regression model, but I have time series. So I have functional variables. So what we can do is to play a little bit with the kernel and try to inject or adapt it using some kind of dissimilarity measure adapted to the functional nature of my input. That's the PhD thesis of José Betancourt. That's a collaboration we did in the past with EMT. And what he proposed is to play a little more with dissimilarity measure adapted to the function. So we have many options to do that. We can define a L2 norm for function. This is what you can see there for the function in green, sorry. But we can also think of high-dimensional time series. So the trick is here to project and reduce the dimension on a first basis. In blue, capital B, and we can define an appropriate dissimilarity function to do the job. And what is nice with that is that we can use standard kernel without any further adaptation to account for the input or the functional input nature. So application, this is an application now in Gavre, in French Brittany. You will travel a lot with me. I have different sites. So here the kind of inputs are manipulating. On the left, you have 7 different time series, 7 inputs which are functional. And the question we asked Rosé was try to predict the flooded area during the different storms on Gavre. So just to have a better picture of what kind of flooded area we are manipulating, you can refer to that. And what you can see there is the leave one out cross-validation graph. On the horizontal axis, you have the truth, the simulated results. On the vertical axis, you have the prediction using the Gaussian process with the dissimilarity measure adapted to functions. So that's already a good result. Check the coefficient of determination, which is quite nice. But what is nicer is if we check now the 5 top model, the 5 optimal model, which are used to do the prediction of the flooded area. If you see a cross on the different columns, and if you have a column termed F, capital F, this means that the functional nature of the input is very important. And what you can see is that for the top 5 models, which are optimized in the sense of the cross-validation exercise, you see that the functional nature is very important. So that really means that we had to adapt the Gaussian process to this case, and this is really the added value of José PhD. So I don't know if I'm okay with the time. Still okay, good. So I'm still listing my challenge. So I spoke a lot about input, functional input. I spoke about what kind of adaptation we can do with the Gaussian process framework for functional input. Now I'm speaking about the output. The output are high-dimensional. You already have a good picture with my video, with my picture. We are manipulating not a single indicator, not a scalar value, but really we are manipulating maps or even spatiotemporal field. So this is illustrated very simply here with another site again. We are traveling. We are on the Atlantic coast. We are not far from La Rochelle. And again, I have on the left the input, the storm condition. And for this storm, we have a flood map on the right. And just to be illustrative, for another storm, we will get another map. And for another storm, we'll get another map, and so on and so forth. And what is important is this number. we are manipulating quantity, output quantity, which are high-dimensional, here more than 10,000 of pixels. So we have to adapt somehow the surrogate modeling approach to deal with such kind of high-dimensional output. So that's a third PhD. That's the PhD of Élodie Perrin. This was a collaboration with Olivier and some colleagues from the CCR, the Reinsurance Institute. So you see here the first steps, again, the design of experiment for the surrogate modeling. This is what you see on the left. Now I have not scalar input, but maps. And the problem comes from the high-dimensional, capital L. So the idea is quite intuitive. If you have a problem of high dimension, you have to reduce somehow the dimension by projecting or embedding everything, the fluid map, in a new space of a lower dimension. That's a dimension reduction step. Once you have done that, for this new variable that we will call latent variable, you can conduct the same analysis by building for each new dimension, each new latent variable, a surrogate model. This is illustrated there by these pictures. And once you have done that, you are able to reconstruct the map for the prediction. So just to have some order of magnitude for the application I'm illustrating here. That's the results of Élodie. She manipulated 200 fluid maps, so 200 synthetic stones. Each fluid map has a size of 2056 times 2056. It's about more than 60,000 of pixels, so that's quite huge. So she conducted the dimension reduction step using a very simple technique, principal component analysis, and you see she reached a new space of latent variable of 2 dimensions, keeping 95% of the variability of those maps. So the reduction is quite huge. And she built, after that, the Gaussian process to predict the latent variables. Oops, sorry. And you see on the map the error, the cross-validation error that she's reaching with such kind of procedure. And we are quite happy because we are reaching, on average, not more than 10 centimeters of error, which is quite okay in terms of predictions. But it's okay, but not enough, actually. And there is different lines of improvement of this approach. Now, if you plot the coefficient of your PCA, so that's the matrix, the scatter plots of the coefficient of your projection. So that's somehow the latent variable that you are analyzing there. You see that your PCA has done a good job because the correlation between the different principal components is 0. The linear coefficient is 0. This is what we are asking for the PCA. But if you see at the pattern, so the scatter plot, here the second latent variable computed against the third latent variable, you see that you have a structure. You have a dependent structure, which is not linear because you are manipulating PCA, but you have a non-linear dependent structure. So the question we ask is, should we inject this dependence information in the surrogate modeling strategy to improve the prediction? So this is what we did, actually. So on the left, you have the results of Élodie. On the right, you have a multi-output Gaussian process approach to do the prediction, taking into account the dependence between the latent variable when we do this reduction, the dimension reduction steps. And you see that we will reach even better prediction error, which is very, very nice for us. Second lines of, is it okay for the time? Oh. 5 minutes. Good. Yes. Second line of improvement. Principal component analysis is very nice, very efficient, very simple to implement, so that's okay for us as engineers. but it does not solve all problems. And the second problem with that is the linearity of these techniques. And this is illustrated with a toy example on the left. So I will do that slowly. I have this is a toy example. So I have a 2D examples. I have the black dots that you can see there. And I'm trying to reconstruct these 2D examples by using a projection on a 1D latent variable. So I'm using a PCA with one principal component and try to reconstruct these 2D examples. So the PCA solution is illustrated in blue. And what is doing the PCA, you can see that the reconstruction is linear. But this is by construction. PCA cannot do anything else but linear reconstruction. And if we want to reconstruct this nonlinear toy example, which is by construction nonlinear, we can use many techniques. And one technique is deep learning and autoencoder. And a typical architecture is on the right. And if we use an autoencoder here with such kind of architecture that you can see on the left, we are able to reconstruct the non-linearity of your data. And what is interesting is if we tune a little bit the autoencoder by using linear activation function, is well known that we can have, again, the linear response of your PCA. So an autoencoder with some tuning can have the same answer as the PCA. So from that, we try to implement that on our cases. So that's another cases, that's Arcachon again. But I wanted to illustrate the added value of doing nonlinear dimension reduction techniques. So on the top, you have the answer with PCA with 90% of explained variance, so a lot of amount of variability explained by the PCA. But the error, but the error is still quite large for us. It's 10 centimeters in terms of reconstruction of my map on two sides on the Arcachon basin. But when using the autoencoder, really we see the benefit of this non-linearity reconstruction because it will really decrease the reconstruction error of the fluid map, in this case, almost close to zero, which is very nice for us. So that was the second line of improvement of the approach. And finally, the last line of improvement is to deal with spatio-temporal response. Not only spatial response, not only fluid map, but fluid map evolving over time. So here we cannot use Gaussian process for the moment. May think about that, but we use deep learning techniques, so convolutional layer for the spatial term and LSTM for the time term. So that's an application for shoreline evolution due to response to tropical events. So maybe est-ce que vous pouviez appuyer sur le bouton pour voir la vidéo? Il suffit de passer la souris dessus et vous n'aurez pas de vidéo, je pense. Ah, merci. So what you can see is on the left the response of your numerical code for some kind of cyclone. In the middle, the surrogate answers, and on the right, you have the differences between the different predictions, which is very, very promising in terms of results for our case. So I'm concluding, if I may. So I show you many sites, many applications, Arcachon, a site in Brittany, a site not very close to La Rochelle. So for us, we really advance on this question of surrogate modeling for coastal hazards in many environments. This is really thanks to the collaboration with Toulouse. So we are very happy because we overcome this problem of functional input, spatial output, but we still have questions about this design of experiment with extreme functional inputs. So that's the job of Nathan, and we are very happy to be to collaborate with Olivier within the PI Learn Water ANITI chair. We still have questions about these spatio-temporal variables, and this is for us still an open question. So we are very happy to collaborate with Yann, with Olivier, with Antoine, who is starting his PhD on that matter. So thank you for your attention.
Many thanks for your talk, Jérémy, which is nicely illustrated. We have time for one question. Yes.
Hello. Yes, thank you for your presentation. It was nice, and I was wondering what is actually your dimension. How do you explain there is only one or two dimension in your PCA that explains everything? What is behind? Is it the altitude or what is it?
That's a very good question, and this is something we do not answer yet. But we see that the latent variable has some connection with some storm condition directly. So we see a pattern directly connected to the storm condition. So maybe there is some physical variable, some mixture of physical variables, which should explain the two dimensions. So, but we don't know yet. And we would be very happy to put some physics on those latent variables. But for the moment, they are data-driven, and we are struggling to extract something physically interpretable from that.
Thanks.
We can take one other question. Yes, Serge?
So I noticed that you moved to the neural network architecture at the end. You are losing the one nice property of the Gaussian process, which is to have an error bar on your result. Is it something that you try to include with your neural architecture? And maybe the second point is on non-linearities. In the introduction, Gaussian processes were for linear PDEs. And I'm wondering whether it's an issue for you, and how do you cope with non-linearities?
Okay. For the neural network, yes, it would be very nice to have somehow an uncertainty quantification framework associated to that. We try to look at what is in the literature for the moment, deep ensemble, for instance, to deliver some kind of realization of the neural network. But we think that it only focuses on one type of problem, the randomness in the nodes in the architecture or the number of layers, but it's not only that. We also have variability in the design of experiment because we are manipulating only 100 of observations, so we have to add that. We have a lot of hyperparameter before that, so the story is quite huge, but we would be very happy to collaborate to see what are the main steps on that. Second question. So we are manipulating PDA for shallow water system. So I think you are currently working on such kind of PDA systems, but they are non-linear.
Yeah.
So to answer the question, yes, we would like to go in this direction, but for the moment, speaking with you, it's not done yet, if I understand.
Not really.
So very happy to further discuss.
Okay, so many thanks to our speaker.